Welcome back to Quantum Computation Simplified Part 8. So in this video we will see why quantum computer has not taken its place or what it deserves, the possible reasons and the solutions and what are the next steps involved. Okay, we heard a lot of good things about the quantum computer, like it can solve a real world problem in a shorter time, much shorter time compared to classical computer. Example, quantum computer will be used to crack RSA algorithm. We also heard quantum computer will solve a real world problem that can't be solved using a classical computer. Example, a new material, the chemical reactions, in biology. But we do not see such things are happening, right? The RSA algorithm has not yet been cracked and it is still being used, and there is no other alternative thing which has come out using quantum computing. AML solution, we still use the classical computer. We don't have an equivalent Keras or TensorFlow in quantum computer. We haven't seen a major breakthrough in chemistry or in medicine, like this vaccine can be obtained in a very short period like that. We have not seen any new material. We heard about development in batteries and display, but all those things are are not happening currently. So does it mean that it is only a hype that we talked about quantum computer? Certainly not. Then what it is? So that's what we'll see in this video. And in order to understand this video, you need a basic knowledge of quantum computing. If you do not have, kindly go through my previous videos, or you can also see any other video or textbook on this subject. It's desirable to have some mathematics knowledge, what has been given in my previous videos, and probability theory also. It will be good, but if you don't have, it's okay. So we'll try to understand what is the reality with respect to RSA algorithm. Okay. We all know that to crack RSA algorithm, we need to find prime factors of a large composite number. Okay, and till date, the largest composite number that has been factored using quantum computer is this number. It's a 13-digit number. Okay, it was done by Zapata along with IBM. And in order to crack RSA 2048, which is what being used now for cryptography, so it uses a very long number, 617 digit number. So we are now at 13, we need to move to 607. And in order to crack that, with the available current knowledge, we say we need minimum of 4099 qubits, theoretically. Of course, it can change or it can come down. So based on this, based on the availability of the quantum computers, people are doing research like when will be able to crack and what is essential for that. So in 2012, Fowler and his team presented a paper in which they said we need 1 billion qubits. Okay, and in 2017, someone came with the idea of 230 million qubits would be sufficient. And later in 2019, they said 170 million qubits. And later part of 2019, Craig from Google said 20 million qubits would be sufficient to crack RSA 2048. So still it's a large number, but if you project in a timeline, if you plot, the requirement is really coming down drastically. You can see here, right? So if you project this, then we may be able to crack very soon. But how soon? I don't have an answer, possibly some experts, but in my view, it may take 5 years, 10 years or 20 years, but not beyond that certainly. So why there is an uncertainty like this? That is what we will be seeing in this video subsequently. And before that, we'll also see what is happening in chemistry. Okay. Major achievements, one would say that Google was able to simulate hydrogen molecule in 2016 using 12 qubits. And then later they were able to study the reaction for hydrogen with nitrogen. IBM performed a quantum chemistry simulation using 16 qubits in 2017. IonQ simulated water, the largest molecule till date actually, yeah, in 2019. So yeah, you may be laughing like, what is this we're talking actually? We are still talking about a very small element like hydrogen in the periodic table, and the smallest, small molecule like water. So, but what is required is you need a very complex molecule to be simulated, right? And if you compare what we have done with the help of quantum computer with a classical computer, we are still, we are in a very old age. For example, Google's project tackled a system that could be calculated with a 1940s era computer. And if we double it, we'll probably go to something like 1980. That's what Babu said. And then, but if you double it again, then probably will be beyond what you could do in a classical computer. And further you double it, you will do magic, you'll do wonders, right? So that is what is the current status. Similarly, Chris Monroe, who is the founder of IonQ, agrees that his team's simulation of water did not match classical machines. But he says that whatever results they got, they are within reach, and simply they require more qubits and running algorithms for longer. Okay. So what does it mean is we are not on quantum computer, but we are not far away from quantum computer. And people are doing a lot of research, okay, on how to improve the number of qubits. But before that, even with whatever qubits we have, we are unable to make use of them effectively. So that is what actually is the main focus of this presentation. And how do we fix that, okay? It's all because we get a lot of errors actually. So that actually puts us into problem. So why? It's because qubits are stable for a very little time actually. It's maybe a few microseconds. Again, it depends what type of qubits, it varies the time. What happens is, suppose you bring the qubit to an excited state like 1. Over a period, it will lose its energy and come to a ground state like 0. So the energy relaxation, decoherence due to noisy environment makes the qubits unstable. Not all qubits can be interconnected. This is another problem, right? When IBM released one of the quantum computers with 5 qubits, you can see here the 6 combinations are possible, 6 interconnections are possible. So what is the use of interconnection? I mean, as I know, actually there are 2 needs for interconnection. One, when you have a controlled gate, like controlled NOT gate and all. Another one, if you want to entangle them, so they should be interconnected. For example, you cannot interconnect this with this. That means you cannot have a controlled NOT gate between this and this qubit. But when IBM released a 53 qubit machine, you can see a lot of interconnections possible, which means we have more freedom to do a complex problem, right? The third point is gates are not perfect. The error rate in a qubit gate is typically like 10 power minus 3. Again, it depends on what type of qubits we are using, right? Compared to that of present day CMOS gate, which is used in a classical computer, it is 10 to the power of minus 19. So that's the reason actually we believe the results coming from our laptop or desktop, whereas the results coming out of quantum computer is a question mark, okay? But you don't have to worry, there are ways to mitigate, right? And measurement error, this is another problem actually. While making a measurement, we may read a 0 as 1 as 1 and 1 as 0. Another important thing is measurement destroys quantum information. I mean, this we have seen in an earlier video also, right? So you cannot in between measure it and then make a correction. So you have to wait till the end. So that makes the problem a little more difficult. But I mean, people are there, great mathematicians, computer science, physicists. I mean, they all come out with a nice solutions. And there are error correction codes available now, and with the help of that, we can make now fault tolerant system. Okay, so that's good news. I mean, since we are talking about the errors, and then whether the number of qubit alone determines the size of the problem to be solved, no. So that's why they defined another term called quantum volume, which takes into account the number of qubits. Of course, that is the most important thing, obviously. The connectivity between them, the crosstalk between them, and gate and measurement errors. So put together, they want to come out with a name called quantum volume. So in fact, middle of this year, Honeywell declared that they have a quantum computer with the highest quantum volume, right? Okay, so we have errors. Now we need to correct them actually. So before that, let's try to understand some terminology called physical qubit and logical qubit. Okay, so the physical qubit is the number of qubits we generate, okay, in a chip or in a different environment. So it can be a superconducting circuit, ion, atom, electron, photon, etc. But a logical qubit is the one which is useful for us actually. Suppose I want to solve a problem. I may solve a problem with 3 qubits. All the 3 qubits should be useful to me. So they are called logical qubits. It's specified as a bit of data used in the computation. And logical qubits should be corrected continuously before, during, and after computation. Okay, then only you will get a right answer, in order to combat the ever-present tendency to decohere. Okay, so this is what we will be doing. And the effect of qubit due to noise is either a bit flip, that is 0 will become 1, or plus and sign change can happen, or we call it as phase, or both can happen. Okay. Like classical codes, we can encode a single bit of data into multiple real qubits. Okay, we bring in redundancy. Unfortunately, like classical computer, we cannot copy the information. Suppose in classical computer, you can have data, you have one more copy, replica, and if anything happens here, you can take the information from the original one or the backed up one. So, but in quantum computer, it's not possible. It's because of no cloning theorem. I mean, if you want to understand, you can Google it and find. Basically, you just can't copy the state of a quantum computer. Okay. Quantum error correction employs syndrome measurements. Okay, we'll learn more about that. So this the advantage of syndrome qubit is it not only gives which qubit, physical qubit was affected, but also in which of the several ways it was affected. And later, with that information, we can correct the data. If error occurs, we can correct it. So that is what we are going to see. So one possible way of correcting is using repetition code. There are many ways. In fact, it is one of the hot topics in quantum computing. How do we correct? So a lot of papers are getting published. You can definitely get into this area. So there are many methods, as I said. Repetition code is one of the ways. I mean, it is also used in classical computing. In fact, many of the classical computing methods can be used, adapted for quantum computing also. So how does it work? So in order to handle a qubit in state 0, so this is what we are interested in. we will have two more redundant qubits or ancilla bits in the same state. That means we'll have three. For every one qubit, we'll have three qubits. Later, when we make a measurement, we'll go with the majority. Okay. So if I get 000, excellent, right? There is no error. But if I get 100 or 010, 001, then I can say that the answer is 0 only. Correct? I'll go with the majority. We assume that the error occurs in one bit, one of the three bits. Okay. Similarly, for handling qubit in state 1, if you get 111, no error. And for any of these three outputs, we can say the value is 1. So with that, what we are going to achieve? With that, the probability of getting the correct value is improved, is increased. For example, if the probability of getting it wrongly once is 0.01, then the probability of getting it wrongly with the 3 qubits is given by this equation, and the value of that is 0.0003. So we are able to improve the accuracy of the result. So this is some simple equation. We can say that if it happens, if all the 3 qubits are bad, then that is given by p to the power of 3. If 2 qubits have gone bad, it is given by p square. At that time, 1 qubit is correct, right? So that's why we have written 1 minus p. And that can happen in 3 possible ways. Like if you take 0 case, it will be 110 or 101 or 011. So that's why that's how this equation has been derived. But as I told you, this works very nicely with one error. Suppose 2 error or 3 error happens, of course, though the probability of that occurrence is very low, but still it can occur. At that time, we'll have a problem. We cannot do anything much about that. So the best way is increase the number of qubits further. Let us see how the error correction happens. So as we discussed earlier, we can detect the error first with syndrome qubits and later use this information for correcting the error qubit. So as we discussed again earlier, data qubit, this is what we are interested to manipulate or to carry. Okay. So we will add 2 ancilla qubits in the same state as the state of qubit which we are interested in. So if it is 0, all will be 0. If it is 1, all will become 1 because of these 2 NOT gates. Correct? So let us say we'll start with 0 and then it passes through some error. Then we'll be able to detect. How do we detect this? We have by using 2 syndrome qubits. Okay, so how do we measure? We have again control NOT gates. By this syndrome qubit gets connected with qubit 1 and 2, and this is connected, the second one is connected with 1 and 3. So we don't have to connect 2 and 3, we don't need another syndrome qubit. In general, if you have n qubits here, n minus 1 is sufficient to detect which qubit has gone bad. Okay, so let us assume that we started with 000, and if you are able to measure here, these 2 bits as 00, that means all are good. No error. And if you measure 01, so when that will happen? When one of them is bad, no. When this is bad, that is third qubit is bad, that is 001, you will get 01. Similarly, when the second qubit is bad, you will get 10. And if the first qubit, our mother qubit, is bad, then what happens? You will get 1 and 1. Okay, because both the syndrome qubits get flipped. Similar thing happens when you use 111. Okay. So we are able to detect which qubit has gone bad, right? And once you have the information, then you can do the correction. So if you get 0, 0 in the syndrome qubits, no correction is required. Everything is fantastic. If you get 0, 1, flip the third qubit. If you get 1, 0, flip the second qubit. If you get 1, 1, flip the first qubit. Very good. So shall we see in real time? I'm sorry. Yeah, we will try to simulate this condition. So I already created a file for you in IBM Qiskit circuit composer. Okay. It's a little bit cluster free. Maybe IBM has to improve certain things here. Too many things are there. Okay. And two things are important for us. This is the circuit. Okay, let me start fresh. Okay, so this is the circuit I made. It has got 4 parts, right? This is the place where we initialize our qubits. If it is 0, no problem. Or 1 means we'll add 1 not. So I'll remove this also. So let's start with the 0, 0. And then this one I just I created this space mainly for adding NOT gate to simulate that there is an error or that there is going to be a flip happening. Okay. And this piece, again, don't worry about this I, it doesn't do anything. Just for better looking of the circuit, I have added this. And this is the place where which qubit has gone bad will be detected. And this piece, this area, we will correct the bad qubit or the qubit which has got error. And this is the result. Okay, it's given in histogram where you will see with 100% possibility. And this gives all the 5 qubits status. And I think you were aware that the Qiskit follows different convention. So the first bit is the last bit here, the least significant bit, and the last bit here is the first bit here. Okay, so we are interested in these 2 bits. That means the first 2 bits we are interested. They are the syndrome bits. So whenever we add an error, let us see what happens. So let me try to add an error in the first qubit. So we are supposed to get 1, 1 here, right? So it's running, you got 1, 1, so it's working, right? And another important thing is, though I have added here an error, it got corrected. So these 3 qubits are stable. They are okay. They are not changed. And if I move the error to the next qubit, I'm supposed to get 1, 0, but because of IBM Qiskit convention, it is 0, 1. Similarly, when I go here, I will get 1, 0. Got it? And same thing works with one state of 1 also. So you will get all 3 ones here. And then if I move this error to 1, you will get all will be 1. Very simple logic. You can see we are using only control NOT gates. Excellent way of correcting. We'll go back to our slides. So we saw that whenever there is a flip happening from 0 to 1, we are able to detect and correct. Suppose a sign change happens, so what do we do? So that also we can do, and one interesting thing is, okay, let me use the pen. This is an important phenomena, that when you applied Hadamard gate on a Z gate, again Hadamard gate, that is equivalent to adding a single NOT gate. So we'll start with a problem like earlier, the initialize, but before doing anything, let us add a Hadamard gate. And if we assume that I mean, not assume, if some error happens in terms of sign flip, then what happens is H sign flip H will become NOT gate. Okay, if sign flip doesn't happen, nothing. Two Hadamard gates will get cancelled and you will get the original state. So this problem of sign flip is converted to bit flip. I hope you have understood, right? So if some sign flip happens, then you will get a bit flip. If nothing happens, you will get the original state before Hadamard. Okay, a very intelligent way people have done it. And afterwards, you deduct with the syndrome bits to get an idea what has changed. And again, using two Hadamard gates, you can undo that, right? Suppose there is a change here, you can do you can undo the sign flip with the help of again this equation. So we are able to do bit flip in the previous slide, sign flip. We converted sign flip problem to a bit flip problem, and then we are able to solve it. Then the next question is, suppose both are happening simultaneously, what we'll do? So thanks to Pete Shore, again you know him, he only made a revolution by his algorithm, right? The source algorithm for prime factorization. So he has also given methods of how to detect and correct the errors when both sign and bit flips are happening. Okay. So again, the only problem here now is, in order to handle one qubit, we need to have 8 more qubits, out of which 2 ancilla bits and then 6 syndrome bits are used. So he uses 1, 4, 7 for sign flip, and then he makes 3 groups, 1, 2, 3, 4, 5, 6, 7, 8, 9 for identifying the bit flip. And once we identify the bit flip, we will be able to correct. I'm sorry, I have not gone into the details. Certainly you can see the reference, but they are very simple, like what we have seen for bit flip. Okay. So with that, now I hope you get a confidence that there are errors, but those errors can be nicely fixed, right? So that's why people are confident that though we haven't seen a big advantage of quantum computers, but we are going to see it soon. So what's the focus needed? This is what IBM was expecting. Not only IBM, I'm sure everybody in the field of quantum computing. So it requires an international effort of scientists, engineers, and the workforce supporting them, as well as the expertise. You need to share your knowledge of, between industry, national labs, students, researchers, and universities in order to build a robust quantum system. So we need to build a strong hardware. At the same time, we should have a very good software. Okay. The next 10 years will be the decade of quantum systems and the emergence of a real hardware ecosystem that will provide the foundation for improving coherence, gates, stability, cryogenic components, integration, packaging. So a lot of research is going on. And as an individual, actually, we cannot contribute much on that unless you are a physicist or, but certainly you can contribute more on the software side. With a systems development mindset, we see quantum advantage in 2020's investments, actually. And a lot of improvements are happening on efficient error corrected quantum circuits, quantum interconnects they are trying to improve, and hardware aware applications are coming out, right? Because we know, we have seen the limitation of hardware a quantum computer, right? So you cannot interconnect every qubit with every other qubit. So knowing that and knowing the problems associated with noise and things like that, people are coming out with hardware aware applications. And certainly that is exactly, I also want you to get into this field. So So we can do a lot of things, and let us try to again see what is being done across the world. So this is the focus. I mean, the people. I mean, released by IBM. The use of IBM computer simulators across the world. You can see. I think one color. I don't know. Remember, one color depends. Sorry. Says about a computer. The other color represents a simulator. And a lot of collaboration also is happening, you can see here. So it's not that people are keeping quiet that I mean quantum computer is not useful. So they are working very hard, and unfortunately India is not doing much on this field. So that is one of the main reasons for me to come out with this series of videos, that people should come forward, because this is going to make a big revolution. So as more and more people started working, then we can achieve that milestone much quicker. Okay. And IBM has also promised that they'll be able to multiply the quantum volume 2x every year. So that is going to be a big exponential change on the capability of quantum computer. And like this, even Google, everybody is coming out with a roadmap. And we have seen quantum volume not only is dependent on the number of qubits. We have to see how effective those qubits are. So we have to reduce the error rate. So with all that, I feel it's still a potential area for every one of us to think. So let's try to do as much as possible. So we don't have to worry that quantum computer is just a hype. Okay, don't think so. It's going to make a big impact soon. So the references, of course, recently CERN, you are all aware, they came out with a nice set of videos. You can go through that, and they have a specific some of 30 minutes on only on error, how to handle. And quantum error correction, there's a nice Wikipedia page to give the basics. And IBM QuizKit has come out with a lot of applications shown here. In fact, they have built models to simulate error. I mean, they've done a lot of work. I'm sorry, I didn't go to the depth of this area. We can do a lot of things, and hope we'll be able to do it soon. And as usual, the Bible of quantum computer, the book by Mike and Ishaq, that also has got a separate chapter on error correction. Okay. So what next? You can start getting into the depth. I think you would have got fairly some idea about quantum computing now, and we can start getting into the depth and then try to build some algorithms. And then you can also see other classical error correction, whether that can be applied for quantum computing. And I'll continue to learn, and I'll also learn some more depth of the subject and come out with videos which will be useful for your learning. Okay, so till then, goodbye. Thank you very much. And I also wish you a very happy, prosperous, and a healthy new year. Thank you.